Very good. Thank you, Olga, for the gracious introduction. This work has been some years in the making, but Olga did a good job of introducing my former collaborators and bosses there at Columbia and MIT. And that story is kind of continued now at San Jose State University. And so I'll be doing a number of different things. I'll be covering some of the fundamental chemistry that was done several years ago, and then kind of refreshing the topics that we've been covering since 2015. The interesting thing is that we kind of went into the project at Columbia not knowing much about nanodiamond. And what we did is we basically referred to the detonation nanodiamond literature for our guidance. But we were dealing with high pressure, high temperature diamond, and we were finding some things weren't really consistent between HPHT and detonation nanodiamond. And that's kind of where the story begins. But for today, the topic is fundamental surface modification and synchrotron-based spectroscopy of nanoscale diamond with bromine, nitrogen, and boron precursors. I just want to let you guys know, for the sake of time, that I won't be talking about the boron-based work, and so I'll be focusing most on the bromine and the nitrogen science. And so let's get right into it. And it's kind of interesting how these things develop over time. And one of my ways of introducing the topic is to consider that starting material. And that starting material, as we know, is macroscopic diamond. And what you have up on the screen right now is the sun-drop diamond. And after we have made lots of money in our startup companies and we've commercialized nanoscale diamond, maybe we can afford the sun-drop diamond, which is only $5 million. And you'll notice that in this beautiful rock, that it's got that gorgeous yellow tone, which we know is due to nitrogen doping of the crystal lattice. And we'll be using that to generate nitrogen vacancy centers, which many of you are familiar with as a magnetic and electric field sensor. But I digress. The original project was actually motivated by the idea of using nanoscale diamond as a neural sensor. And so I entered into the project as this kind of go-between. The project had engineers and physicists, myself as the chemist, the physical chemist, and then I was also interacting with neurobiologists. So I was kind of acting as this path between the language of the physicists and the engineers and the neurobiologists. And a lot of this was summarized by a collaborator, Rafael Yusta, who's the last author on the brain activity map project. And so this whole idea was, can we use NV centers to be able to track the electric field of firing neurons in real time? And so one of the quotes from this particular summary is talking about the development of tools. And I'll give you this quick quote from Freeman Dyson, and I think you can kind of encapsulate it in your own mind, how you do your own work when it comes down to applications from fundamental science. And the quote goes like this: "New directions in science are launched by new tools much more often than by new concepts. The effect of a concept-driven revolution is to explain old things in new ways. The effect of a tool-driven revolution is to discover new things that have to be explained." And I think in many ways, that is like one of our fundamental callings in science and in engineering, is like, we don't know what we don't know because we don't have the tools in order to probe, to look into different systems. And of course, for neurobiology, there's many things that we don't understand about the human brain and the connectome, the way that neurons are actually programmed inside of our brain to allow the storage of memories, the retrieval of memories. And so there's many applications when it comes down to people who end up with traumatic brain injuries. Why does one person recover quite quickly while somebody else does not from a car accident in which their brain has been injured? So this kind of far-flung idea that we would use diamond and actually put diamond into neurons is kind of the original motivation for this work itself. Now, what's interesting, before I left Columbia and MIT, we did have some relatively good staining of our neurons, and you can see that in this particular image right here. This is scanning confocal work where you're doing a Z-stack. And what you can see is that the diamond is going up the axon and then into what's known as the axon hillock, which is right before the neuron body. And then you'll notice that the diamond itself did not penetrate or was not endocytosed by the neuron, which we found that to happen before. This was actually done with silica-coated diamond, which was our first chemistry that we did on these materials themselves. And if you look over on the right-hand side, we basically zoomed in a little bit more to look at the dendrites and did scanning confocal work on those dendrites. And ironically enough, we could place about 1 to 2 nanodiamonds within the area of these dendrites. For those of you who are unfamiliar, dendrites are the locations of chemical receptors that make neurons fire. And in this particular case, we could use a correlation spectroscopy to identify what's known as a G2 dip. So we know within that diffraction spot limited size that we had approximately 1 to 2 NV centers within that area. And we knew that we needed to have very few diamonds in there if we were to watch this firing of the neurons in real time. I can tell you though, even though this sounds rather fancy, it's been 5 years later, and I don't think from the MIT side and the Columbia side that they have shown that the NV diamond is a robust platform for watching neurons fire in real time. And I think one of the reasons is it's very difficult to locate the diamond inside of the membrane. And so I'll kind of leave it at that. But if you were to look at the labeling of a dendrite with green fluorescent protein, which is what we have on the left-hand side, and compare that to NV center diamond, which is over on the right-hand side, many of the features that you'd be able to identify with a neuron, the dendrite itself and the axon hillock are available. So I'll leave that for another discussion for those who are really into biolabeling. Most of today's talk, though, will be in fundamental surface science. And so I would ask this question, can we direct a nucleophilic attack of the surface carbon on these diamonds? And I'll get into some of this oxidation chemistry, but I'll do a preamble and say, can we remove the carbon-oxygen bond from the surface? So kind of keep that in the back of your mind as we progress through today's talk. Now, many of you in the audience, of course, work with diamond, are interested in diamond, but I wanted to have this general summary slide and say, well, what are the different types of diamond, and why would we be using each one of these different types? Of course, we know that diamond has an all-carbon matrix and is non-cytotoxic. That's why these biological applications are so important. We know it's chemically inert, and we've got these beautiful thermal conductivity properties, which allows it to go to thermal equilibrium with its surroundings very, very quickly. And of course, it's optically transparent if it doesn't have a high level of doping in it. Now, many people are used to seeing the detonation nanodiamond work just because it was it was been done for a longer period of time, and as far as I understand, was originally invented by Russian scientists, I believe in the 1960s. And that's been like a robust platform for looking at diamond nanocrystals. Of course, there's also evidence of finding them in meteorites. On the right-hand side, we have our chemical vapor deposition diamond, where you can have purified diamond samples free of nitrogen-14 and other impurities, free of the nitrogen isotopes that might mess with the spin properties of NV centers. But in the middle is kind of our bread and butter, and I think many people in the room do research with the high pressure, high temperature nanodiamonds. And as we can see, they've got this kind of shard-like appearance to them, and that's due to the ball milling process, as you're aware. Now, with our NV centers, which are hosted within the diamond, and of course we can go back to that sun-drop diamond, we know a couple of different things because of the fundamental work on NV centers. We know they can readily absorb visible light, typically 532 nanometer laser light. And we realize that the extra electron, when it's sitting inside of the NV center, creates this ground state triplet. Now, the ground state triplet has these unique properties, which are summarized in the electronic configuration energy level diagram in the bottom left. We can, of course, split and initialize the electron into either the 0, +1, or -1 state. And of course, a lot of powerful work has been done to understand the properties of the NV and its surroundings itself. For biological applications, people have enjoyed the fact that it's an infrared emitter, and we can see in the right-hand side that we've got the NV0 emission, which starts at 575 nanometers with the zero phonon line, and then for NV- with the ground state triplet, its zero phonon line is at approximately 637 nanometers. If we are to place this nanoprobe with this quantum information processing unit, the NV center, it is going to be necessary for us to tune and engineer the surface properties so that we can have a high level of control. Now, one thing that I think is interesting is that switching between the NV0 and the NV- and the connection to the surface termination of nanoscale diamond. And of course, most work has been done with carbon-oxygen terminated diamond and hydrogenated diamond. And for carbon-oxygen, typically you have more of a NV- charge state probability. And then if you hydrogenate the diamond surface, you're more likely to have NV0 properties. What I think would be interesting is to tune the surface properties to allow that switching to happen very, very quickly, so you could develop a more sensitive electric field sensor. So on the left-hand side is some older data from NV diamond that was used for HeLa cell staining, and you can see some of the dips that happened during the application of the radio frequency and toggling from the 0 to +1 and -1 charge state. Everybody should be fairly familiar with this data. This is relatively old. What was interesting in this HeLa cell staining is that they didn't modify the diamond. It was basically like a shake and bake type of experiment, and therefore things were not targeted. In the case of using bulk diamond, many of the properties are much more well controlled, and John Manim and others at IBM published in 2013 doing NMR spectroscopy and doing it on a very small number of molecules. I think it was 10 to the 4 or 10 to the 5 molecules, and basically being able to replicate NMR spectroscopy at room temperature. Now, on the right-hand side is the work that my colleagues and I did at Columbia and MIT. Now, just to highlight that the work on the right-hand side did not use a microwave source. We did not toggle the NV centers into the +1 or -1 charge state. The right-hand side work is done purely by just reading out the fluorescence. And so we used a spectroelectrochemical cell which is on that right-hand side, and then we toggled our voltage, which you can see in the sawtooth pattern, and then watch the fluorescence rate of individual NV centers in real time. And we used a model, which is down in the bottom left, which basically used an argument for band bending and the Fermi level changes of the diamond and its influence on the NV center, basically saying that we are switching, readily switching the NV charge state from NV0 to NV minus. Now, if you were to read this paper in depth, what you would see is that the absolute number of particles that actually blink, that respond to the voltage, was only about 20%, 25%. And the issue here is that most of the NV diamond was stable in its fluorescence and didn't respond to the voltage. And so that really got my mind going that, well, perhaps the surface structure of the NV diamond has not been destabilized enough to allow for that charge switching to readily occur. So I want that to be another kind of thought in the back of your head, that even though these results are quite promising for using NVs as electric field sensors, the absolute efficiency was relatively low. And so I want to just put that into context. And I don't usually use the pen. Let's see if the pen works. All right, you guys can see that on your screen? That has to be up there, I'm assuming. Okay, very good.
Yep, it's worked.
Okay, awesome. Thank you so much. I don't typically use that feature, but I think I will for today. So, we have open challenges in the high pressure, high temperature nanodiamond field for surface modification. We know when we oxidize these nanodiamonds that they're electrostatically stabilized. We also know that if we were to put them into buffer or cell culture media, that they readily aggregate and fall out of solution. So we need to be able to manipulate the surface structure. We need to be able to control the diamond surface with a level of atomic and molecular specificity. From my looking over the literature, it looks like most researchers, for good reason, target the carboxylates on high pressure, high temperature nanodiamond after the acid-base acid chemical protocol. But I think it's fair to say that there's a lack of robust chemistry to remove alcohols on the surface of the diamond. And the alcohols, being not only not very reactive, they also are extremely stable. They have a bond dissociation energy of over 1,400 kilojoules per mole. And so I think it's a really exciting time for us to explore chemically this field, and hopefully the applications in biolabeling, quantum communication, biosensing, and magnetometry will continue to evolve, where we can actually have real impacts from our work. Now, in kind of the overarching number of techniques that are used, and for those of you who might know about the show Breaking Bad came out when I was still in graduate school, so I'm giving a little nod to the Breaking Bad folks. I thought that was a pretty interesting show, especially when I needed to get out of the lab to relax a little bit. And of course, folks, if there's any questions, you want me to go over something more thoroughly, you don't have to wait till the end. You're more than welcome to chime in, and I can answer any questions you might have. But as you can see, we use a host of different techniques, from Raman to XRD. NEXAFS is near edge X-ray absorption fine structure, though typically we just say XAS for X-ray absorption spectroscopy. XPS is our photoelectron spectroscopy technique, and then DRIFS is diffuse reflectance FTIR. And so we always want to use that trifecta of techniques, XPS, XAS, and DRIFS, to be able to do thorough chemical analysis on our samples. And so to review some work that was published quite a while ago, this was our initial understanding that detonation diamond and high pressure, high temperature diamond was not acting the same. And so in that upper picture, you can see the starting material, which is our bulk HPHT nanodiamond. You can notice that it's got that beautiful yellow tone. This is what we purchase from any of these companies. And then we purified it at different temperatures over 2 hours. And so we use Raman to track the purification process. On the left-hand side, you can see that we've got two different Raman spectra. They're dominated by the breathing mode of the diamond at 1332. You'll notice that this spectra was done at 633 nanometers and has additional features besides the bulk phonon mode. But if we were to take that and blue shift it to 325, these additional features in this area and this area drop away. The reason for that is that the SP2, SP3 Raman cross-section for scattering is 1-to-1 at 325 nanometers, but the SP2 is about 50 times more sensitive at the visible wavelength. And we always were of the opinion that these additional modes were actually caused by Pandy chains, reconstruction of the diamond surface into SP2-like chains. But if we were to compare our sample for HPHT versus detonation diamond, we found that the relative signal and the width of the peaks in detonation diamond were not comparable. And so what we assumed is that the detonation diamond had crystallographic and phononic properties that were very different from HPHT and of those of bulk diamond as well. And so we did some controls. We looked at HOPG because we wanted to make sure that we didn't have a graphitized surface. And in fact, the features that we were finding did not match up or align well with a graphitized surface. And that gave us the impression that these additional features in this area after aerobic oxidation may in fact be due to these Pandy chain reconstruction. I think one thing that we always want to compare to is for a single crystal diamond slab. And you'll notice that the diamond slab, and this was done at 633 nanometers, is almost indistinguishable from HPHT nanodiamond at 325 nanometers for that Raman signal. So this basically told us that detonation diamond and HPHT were not a similar material, even though they were both diamond. So that was a revelation to us because we assumed all diamond was diamond. And later on, high resolution TEM was used to analyze the expressed crystallographic facets. And as many of you know, the expression of the facets is usually dominated by the 111 crystallographic facet. And that was always quite curious to us why that in fact happened. And it is important because then that tells you how many dangling bonds you would find on the diamond surface. The relative expression of 111 is quite dominant. And we didn't quite understand why that happened until we looked at when we would end up breaking the 111 crystallographic plane. And so in this theoretical study of strain versus stress and the actual breaking of the diamond itself, you can see that the 111 crystallographic facet ends up cleaving with the least amount of strain. And then the 110, and then eventually the 100. So during the ball milling process of the bulk high pressure, high temperature diamond, similar to taking a rock to a jeweler, a jeweler will go ahead and cleave the diamond planes using a hammer along the 111. And even though we're looking at nanoscale diamond, the same physics is occurring. Why is this important for us? Well, the 111 is a single dangling bond surface and therefore should only be able to accommodate one sigma bond. On the other hand, the 100 is a double or has two dangling bonds and could potentially have a C double bond O, a ketone, for instance. And then we would have to have 3 dangling bonds if we were to support a carboxylate and have our carboxylic acids on the surface. And so we wanted to make sure that we could verify our post-oxidation diamond chemistry very, very thoroughly. And so we end up using a number of different techniques. This is a summary of X-ray absorption spectroscopy. In XAS, you are taking core level electrons and taking soft X-rays. For nitrogen, that would be around 390 eV, and you are photoexciting them from the 1s into some 2p state, something that has an angular momentum change. So the rules for XAS is that you need to change the angular momentum to plus or minus 1. Now, this is a surface sensitive technique and it's element specific. So we can look at carbon, nitrogen, boron, oxygen individually and be able to cross correlate what's going on there. That photoexcited electron is then collided with another core hole exciton and then is emitted from the surface of the sample. So typically we can probe anywhere between 5 to 10 nanometers into a sample itself. We do this at the Stanford synchrotron radiation light source. Many of you are familiar with synchrotron radiation. It's basically an artificial sun where we've got near relativistic energies of the electrons moving around the ring. As they decelerate going around the ring, an amazing amount of light is released. The particular station that we use is approximately in this area. That's where 8-2 and 10-1 happen to be where we work with Dennis Nordland and Sanjung Lee. And so at this beamline, we can look at all of the low Z elements as well as transition metals. As you can imagine, I'm not the one manning the beamline all of the time. So here's a picture of my students running the beamline experiments, writing macros, problem solving. Recently, we actually ran a beamline run remotely, which was new to us because of COVID. With any of this information, we can readily quantify the content of the diamond. And one of the things that we originally found, and this was the first observation of the diamond core hole exciton in nanoscale diamond, was this feature at 289.0 eV. And this let us know that the electronic structure of the nanoscale diamond was almost identical to that of single crystal diamond itself. And so that kind of continued to build up evidence that we had something unique going on with the system itself. And if we were to go ahead and look at the amount of amorphous carbon, the amount of amorphous carbon was relatively small in the system. But what we wanted to do was really look at those carbon-oxygen bonds. You'll notice as we increase the temperature of oxidation from 475 to 575, that the amount of pi star C double bond O, which would be due to ketones or carboxylic acids, does not increase. In fact, it decreases as the oxidation temperature is increasing. Well, why would that be the case? We believe that the reason we ended up with these decreases in ketones or carboxylic acids was because we were cleaving those bonds. Those unstable carboxylic acids were being purged from the diamond surface and leaving the most stable moieties. And we would argue that the most stable moieties available to us would be those alcohols. The alcohol groups supported along the 111 crystallographic facet because it can only support a single sigma bond. So this is the kind of mind frame that we wanted to use to be able to manipulate the surface. We wanted additional techniques to support this type of conclusion. Of course, FTIR is much easier to use than the synchrotron. And so we did FTIR, which supported this assignments. We've got large alcohol peaks versus relatively small carboxylic acids. If we did a pre-Piranha etch and then did our aerobic oxidation in the tube furnace, we could actually eliminate most carboxylic acids on the surface. If we were to quantify it, if we were just using aerobic oxidation, we summarized that we had about 30 alcohols for every carboxylic acid. And then if we did the piranha work, then we could increase that ratio to about 90 to 1. And so at SJSU, when we do our chemistry, FTIR is typically our bread and butter because it's right there in our lab and it's easy to access. Now, if we were to go to the synchrotron, you can actually do XPS with different wavelengths of radiation, and that's what we have here on the right-hand side. This is wavelength-dependent XPS at 410 and 950 EV. The way that you can understand it is 410 EV light would be more surface sensitive. You end up going down to about 3 crystallographic facets, while 950 EV gets you down about 1 nanometer into your material, approximately 5 to 7 crystallographic facets into the material. But overall, it supported our conclusions that we had very few carboxylates and a mostly alcohol-rich diamond surface. Now, overall, what chemical approaches are needed to modify these inert diamond surfaces? Well, the answer for us and the way that we view it is that we should be targeting tertiary alcohols and not carboxylates. So the work that we've been doing recently does not use carboxylate-rich diamond, but instead is the direct product of the aerobic oxidation. Now, our view is that we need to use small molecular precursors to fit into the sterically hindered and chemically inert system. Now, previously, before I got into the diamond game, I was doing a lot of work with cadmium selenide quantum dots. And I think this is an interesting table. If you look at the crystallographic expression of surface groups, and we can focus on the 111, the cadmium selenide crystallographic facet only has about 6.5 atoms per nanometer squared. On the other hand, diamond has 3 times the number of surface carbon groups and is very, very tight in order for any chemistry to occur. So the overall steric hindrance and crowding is incredible. And so we wanted to focus on purely low Z components, everything in the first row, boron, oxygen, carbon, and nitrogen. So when we do our work at San Jose State, my lab is separated into about 4 thrusts, going on to 5 thrusts. And we're focusing on amine chemistry, silica chemistry, and boron chemistry. For today, I can't really get into much of the silica chemistry, even though it seems to be the most robust way to modify the surface of the HPHT diamond. The boron, I can give an update on boron in the near future. But for today, I'd like to talk about the amination chemistry. And this amination chemistry is largely failed when we wanted to do direct amination. So we went ahead and we took oxidized diamond and tried to do direct amination in a tube furnace, going from 300 degrees C all the way up to 1100 C in an ammonia environment. And to say the least, we failed. And we got very low amination rates. So we knew that we needed to activate the surface to cleave and remove that carbon-oxygen bond. And so on the left-hand side, you can see the alcohol-rich diamond lattice. And then we're doing this activation chemistry with SOBr2, thionyl bromide, which is a very strong and nasty brominating agent. And after we've done the bromination chemistry, we want to go ahead and aminate the surface. Our bromine should be a good leaving group and allow for the amines, a carbon-nitrogen bond formation, to occur. And then once we've got our aminated surface, we can then go ahead and do linking chemistry. And in this particular case, we decided to do folic acid because it's overexpressed. There's folic acid receptors on cancer cells, so we wanted to use it as a test bed to say that the amines on the surface of the diamond are still viable for functionalization. And we're using XPS, we're using XAS and FTIR to probe these samples. And in particular, this is a interesting piece of data that I want you guys to see. This is known as a RIX map. And let's kind of look at a RIX map in a little bit more detail. A RIX map is a resonant inelastic X-ray scattering profile. So you've got the emission energy from your sample, and then you've got this excitation energy. So it's kind of like a combined absorption and emission data plot at the same time. If you were to integrate along the y-axis, you can then go ahead and extract out your partial fluorescence yield XAS. Basically, the electronic structure in the excited state, similar to the diagram that I showed you. And then if you were to integrate from left to right along the emission energy at a single excitation energy, then you're able to extract out the XES, the X-ray emission spectroscopy, or the occupied density of states in the ground state. And so this data is actually collected on beamline 10-1 in the transition edge sensor, which is a state-of-the-art X-ray detector. The TES is a very fancy thermometer that's held at 60 millikelvin. And when the X-rays strike the detector, it slightly raises the temperature of the detector. But this is the reason it's called the transition edge sensor, is that it's right on the transition edge between superconductivity and not being a superconductor. So when you change the temperature from the impact of the X-ray, it changes the temperature and therefore changes the resistance. The resistance then changes the current that's passing through the detector and is proportional to the original X-ray that struck the array of pixels in the detector itself, which, interesting, we don't need any type of diffraction grading. We don't have to separate the incoming X-rays. We basically just track the process by the temperature change, which is occurring in real time. So you can flood your sample with all of these X-rays and basically get the full information from your sample in real time and get zero background. This particular detector does not have background counts associated with it from superfluous carbon, which is really important for us for boron and nitrogen data collection, because carbon background signal is always getting in the way. So imagine that we've done the X-ray absorption process, and then there's the emission process. That TES detector is coupling both of those things together so that we can both get our ground state electronic configuration and our excited state in one shot. So it's quite powerful, and we're very thankful that we get to do this work at SSRL and work with our collaborators there, because it really gives us definitive information about what's going on with the diamond itself. Now, what you may be wondering is, well, what's going on with the bromine chemistry? And that's really the bread and butter and the difficulty with this system. On the left-hand side, we would key in on this carbon-bromine stretching mode. And we did this with pyridine and without pyridine. Pyridine would be a catalyst to increase the bromination rate. And basically, we found that with pyridine, we could catalyze the bromination and get better turnover and purging of the carbon-oxygen bonds. You'll remember right here is where you would typically see your alcohols. And overall, we found that if we were to go ahead and do many purification cycles of these samples, that we would actually debrominate the surface. So it's highly sensitive. The actual purification process in and of itself decreases the bromine of the surface. On the right-hand side, you can see that we verified this with XPS. We had to use an inert atmosphere chamber. And basically, we saw the telltale signs of direct alkyl-bromide formation on the surface of the diamond. And then with XAS, we found new features that we assign to a sigma star carbon-bromine bond, the alkyl bromide, and what we believe to be an acid bromide, which is occurring at approximately 287.5 eV. You'll notice that those features after the amine chemistry, and this is done with a simple amine, this is done with ammonia dissolved in THF, that these features are removed. And so that's kind of where the difficulty began, was the ability to readily control the bromination. And what we found is that this bromine does not want to stick around. We would argue that the bromine is so labile that it can even debrominate in inert atmosphere over, a couple of weeks. So we have like a window of time in which for us to use these bromines. The data on the right-hand side is after we've exposed our brominated diamond to open air conditions. So we loaded a drifts chamber. We brought it over to our FTIR. We took our original inert atmosphere FTIR, and then we opened up the chamber to oxygen. As soon as we opened up the chamber to oxygen at 25 degrees C, we immediately see debromination, immediately. And this basically takes less than 2 minutes for us to see the carbon-bromine bond being broken. And this is in, basically just the humidity inside of our room. And so we could track this in real time. As soon as we hit the go button on our spectrometer, we could instantly see this type of decrease. Now, what's interesting, and this is something that I want you all in the audience to pay attention to, even though the carbon-bromine bond is decreasing, you don't see any change in where the alcohol groups, or where you would assume there would be a type of ether linkage, a carbon-oxygen-carbon linkage to occur. So our running hypothesis is that this can be understood by pseudo first-order kinetics, and that we see a kinetic rate of about 7 times 10 to the minus 7 inverse seconds. And so this is occurring in what we believe to be almost like an evidence of a carbocation intermediate. The bromine is being released, but we don't readily see the formation of new alcohols. It's not as if one is going down and the other is coming up. So what's going on there? We believe that the hydroxylation in open air conditions must be happening slow. So we have our brominated surface. It's being exposed to open air conditions. It's debrominating, leaving this carbocation intermediate. If there is very little water in the environment, well, then it takes a relatively slow period of time. Who knows, maybe even a couple of weeks to reform the alcohol-rich surface. On the other hand, if we were to do it in neat water, within 1 minute, we can go ahead and regenerate our alcohol-rich surface. So this is our starting material in purple. This is our brominated sample in red. And then in black, this is after we have reacted our brominated sample with neat water, allowed it to react for only 1 minute, and then purified it, and then did FTIR once again. So you can take it for what it is, but I think this might actually be evidence for a long-lived carbocation intermediate on the surface of our high-pressure, high-temperature diamond. We also found that this carbon-bromine bond in inert conditions, in nitrogen, and this is where we're using temperature-programmed desorption spectroscopy, that we can cleave the carbon-bromine bond at about 80 to 90 C. So even before you would have the desorption of water from a sample, we're already breaking the carbon-bromine bond. So overall, this isn't behaving like a normal 1-bromo-adamantane sample. The stability of the carbon-bromine bond is much, much different than what we would expect through normal small molecule chemistry. And this is quite confusing unless you take into consideration the fact that we have this highly sterically hindered surface, the surface of the diamond itself. And so we replace these small alcohol groups with the bromide ion, which is 80% larger in its atomic radii. Therefore, the more bromine that you place onto the surface, the more destabilized they're going to become. And so this can be viewed as either a deficit or an asset. And I haven't been able to plot up some recent data, but we've almost been able to completely purge all of the alcohol groups from the surface, and had almost 100% conversion of the alkyl-bromides on the surface. And it really comes down to not purifying the sample as much, ironically enough. So we would we would kind of summarize the thermal desorption of the bromine groups at 90 C. We can see this happen in seconds. We've reached the dissociation energy, and off they come, which is obviously much different than the alcohol groups, which don't come off until 700 C. On the other hand, if we were to store our sample in our glove box at 25 C and we came back and did FTIR, those carbon-bromine bonds have gone away, and we can't recover the sample, and we'd have to basically start over. So there's a window of opportunity in order to do this work. Once the bromine has been generated, that's when we need to get to work to do the emanation chemistry. We used a number of different amine precursors, the simple of which was just our ammonia and THF. We did other branched amines as well, and alkyne-amines. And so I would argue that our chemistry is reliant upon this carbocation intermediate, the leaving of the bromine in the presence of some nucleophile, and then we've got our nucleophilic attack of our long-lived carbocation intermediates, and then we would have a removal of a leaving group of hydrogen bromide. We can verify this using X-ray absorption spectroscopy. It appears that we've got a mixture of different bonding environments. It looks like we've got doubly bound carbon nitrogen bonds. That should actually be a pi star. And then we also have sigma star transitions, which we assume, of course, to be our amine groups on the surface of our diamond itself. So this is done at 25 degrees C in anhydrous conditions. And so the presence of water is not favorable. And of course, all purification is done in a glove box environment with desiccated solvents. Of course, we don't just use our XAS to verify this. We also use XPS. We verify that we can see a majority of the surface is dominated by our amines, and we have some amount of imide bond formation, but it's relatively small, which is consistent with not having many carboxylic acids. So we have very few acid bromides. Most of it is being dominated by single carbon nitrogen bonds on the surface itself. So I'm pretty sure I'm running over in time, and I certainly am. I apologize for going over. The conclusions that we can say is that we've realized a metastable brominated nanodiamond surface. This bromide is highly unstable. It's unstable in air. It's unstable at high temperature. Even though I didn't get into a lot of the details, I think we can also say that there is some evidence for a Williamson ether-like reaction. And this is due to some FTIR evidence that shows that we've got ether linkages on the surface. The emanation was facile due to the instability of this brominated diamond surface. And this particular spectra, and I didn't really have time to get into it, this RIC spectra is actually done with a brominated surface and an alkyne, an aminated alkyne. And this actually gave us 11 times higher amination rate than what we found with the ammonia. Of course, we're always going to use multiple techniques to verify the chemistry, and we are adamant to make sure that we are very careful prior to making any of our claims. In the bottom right-hand side, you can see the drifts of our starting material, the brominated material, and then after the amine chemistry. And so we've got some telltale signs of the transition between an alcohol-rich surface to a brominated surface, and then to one that has many amines on the surface. This is kind of a summary of the increase in the signal with that alkyne-amine. And of course, I'll be more than happy to discuss some of those results. Of course, I didn't do the work. These are all of my researchers. Just to let you know, San Jose State is a primarily undergraduate research institution. Everybody that you see on the screen is an undergraduate. They go to the foundry, they get trained, we go to SSRL, we run our experiments, and so it's quite exciting. Many of my students now are in PhD programs around the United States. Jocelyn recently was awarded a NSF graduate fellowship, and I'd like to really thank collaborators Peter Sigler, Virginia Alto, and Dennis Nordland in Prague, the Molecular Foundry, and SSRL. I'd also like to thank our funding from the NIH, the Department of Defense, and all of the support we've received from Department of Energy facilities. And with that, I thank you very much for your time and your patience, and I can take any questions you may have.
Abraham, thank you very much for your very interesting talk on this new bromine chemistry. So it's definitely, for me, it's all new information, and with all these great details and new perspectives, how easily you can now aminate nanodiamonds with presumably very high degree of amination. It's extremely important for the field. So thank you very much for presenting this new unpublished data, actually, in effect.